We will be seeing the m-derived high pass filter. So we can use either T or pi similar to the low pass filter, but the only difference is that here Z1 will be becoming capacitance and Z2 will be chosen as inductance. So with that difference only we can achieve the characteristics of high pass filter, which is different from the characteristic of low pass filter, right? So all these things are same except this Z1 and Z2, right? Make a note of it. Fine. Okay, so here also we will be having resonant frequency, because that is the reason we are designing m-derived filters for getting the sharp cutoff, right? So in case of T section we will be getting series resonance, and in case of pi section we will be getting parallel resonance, at which the attenuation is going to become infinity. Fine. So similar to the previous conditions for low pass filter, we can get the resonant frequency, which is nothing but the frequency at which the infinite attenuation is going to occur. So when you put the condition of resonance, that is inductive reactance is equal to capacitive reactance at a certain frequency known as resonant frequency, that is omega naught, you will be getting this relationship between f naught and m, l and c, right? Okay, so for a high pass filter we got the cutoff frequency formula from the constant K filter, that is 1 by 4 pi into root LC. So but here f infinite for m derived filter is going to become fc into square root of 1 minus m square. So accordingly we can choose m for the required f infinity and fc, right? So this is what we get for high pass filter of T section. So if you observe, the series impedances are capacitive, and that means Z1 is capacitive and Z2 is inductive, L by M. Right? Okay, now the M derived T section high pass filter is shown here. Okay, so similarly we can get M derived pi section, and the resonant circuit is formed by the series arm, inductance and capacitance, but it is of parallel resonance. Okay, that is also like that, also you can remember. In the series arm we get, then it will be parallel resonance, that is with respect to pi section, and in case of T section we are going to get resonance in the shunt arm, and that is series resonance, right? I think this is an important thing here to note. Okay, then with the pi section again you equate inductive reactance and capacitive reactance, you will be getting again f naught, and if you relate that with respect to f infinity, both will be equal, and that is in terms of m and lc given like this. Now for a high pass filter we have fc, that is cutoff frequency. Now we can even relate the cutoff frequency and f infinity as before. So in that particular case you will be getting m in this manner, right? So from these conditions the m derived pi section high pass filter is shown, and the variation of attenuation, phase constant as well as characteristic impedance with respect to frequency are shown in these figures. And the attenuation is rising abruptly, because that is the reason for going for m derived filter, and if we choose m appropriately we can get the attenuation rising abruptly, and it becomes infinite at f infinity, which is nothing but resonant frequency, and then decreases, which is nothing but sharp cutoff. Fine. So this is about the m derived high pass filter, both T as well as pi section types. So we are getting the sharp cutoff here in this region, and the phase constant variation is given like this. Till f infinity it is 0. From there to fc we are having the phase of minus 180, right? And we are having the variation of z naught, and both the variations for pi section as well as T sections are shown here, similar to the all other filters that we have discussed, right? So the use of m-derived and constant K high pass filters in series gives a sharp cutoff and high attenuation in the entire stop band. So this is going to be done with the cascade connection similar to the low pass filter, so which is not required in this course. Right? Fine. Thank you.